Hello, everyone. This is George Pavlidis from the ARGUS Horizon Europe project. I will be your host for today's event. Today's event is a joint event organized by the Green Cluster on Cultural Heritage Protection. This is a joint dissemination webinar organized by four projects, for Horizon Europe projects: ARGUS, NERITES, ChemiNova, and iPhotoCult. The title of this webinar is From Heritage Data to Heritage Intelligence, early results from European cultural heritage monitoring projects. First of all, I welcome everybody in this meeting. I hope it's a fruitful meeting for everyone and we all learn something. On behalf of the Green Cluster in Heritage Protection, I would like to warmly welcome you to today's joint dissemination webinar. As you all know, cultural heritage is increasingly facing complex challenges arising from climate change, environmental pressures, natural hazards, human activities. So it's a multifaceted, challenging environment, but today we have a lot of possibilities on our side. At the same time, we have rapid advancements in sensing technologies, in Earth observation, in artificial intelligence, and digital technologies, which are opening now entirely new possibilities for monitoring, understanding, ultimately protecting our shared heritage. So today's webinar brings together four Horizon Europe projects that approach this common challenge from complementary perspective. That's very crucial for this webinar, and it is a key point for this event because all four projects, although focusing on the same topic, protection of heritage, they are completely complementary with very little overlaps. Although each project has its own objectives and scientific focus, we all share a common ambition to transform high-quality observations and scientific knowledge into practical tools that support more effective, sustainable, and evidence-based heritage preservation. During the next minutes, you will hear about ARGUS, ChemiNova, NERITES, and iPhotoCult. Specifically how ARGUS is integrating monitoring data into digital heritage intelligence, how ChemiNova is advancing the digitalization and monitoring of heritage threatened by climate change, how NERITES connects underwater cultural heritage monitoring with marine policy needs, and how iPhotoCult is developing advanced non-invasive imaging technologies for cultural heritage diagnostics. We hope these presentations will not only provide an overview of the progress achieved by each point, which is a main point in this event, but also to stimulate discussion and sparkle future collaboration across disciplines and projects. The agenda for today is here for you to see how it goes. First, we have a presentation for ARGUS. The presentation is titled From Monitoring Data to Heritage Intelligence, Lessons from the ARGUS pilot sites, and it's going to be presented by me. Then from ChemiNova, the presentation will be by Marta Segovia, and it's going to be titled Progress in the Digitization and Monitoring of European Cultural Heritage Threatened by Climate Change. Third is the presentation by Elena Telegrafou from NERITES. The presentation is titled Bridging Underwater Cultural Heritage Protection, Marine Monitoring, and Policy Needs. And last but not least, iPhotoCult, represented by Eliana Piryanaki, is going to present non-invasive photoacoustic imaging for in-depth cultural heritage diagnostics. So I hope you all set. Everything is working perfectly for everyone. We move straight to our agenda and the first presentation, which is by me regarding how we envision to move from monitoring data to heritage intelligence within ARGUS. ARGUS stands for non-destructive, scalable, smart monitoring of remote cultural treasures. So ARGUS is focusing on remote heritage. Why ARGUS was ever proposed and is being implemented? We all know that climate change accelerates deterioration. The threats increasingly interact or act simultaneously rather than occur in isolation. Remote sites are difficult to inspect continuously. Monitoring alone does not provide actionable knowledge. So preventive preservation requires continuous evidence. Preventive preservation requires understanding long-term risk evolution. Preservation is becoming, in a way, a dynamic rather than a static problem. So these are reasons why we thought ARGUS should be proposed, and it was funded and is now being implemented. The ARGUS ecosystem includes 5 pilot sites across Europe. You can see in this map how the pilot sites are distributed. We have the Delos Island in Greece, a complex landscape in Monte Lucretili, the Abbey of Sant'Antonio di Raverso in Italy, northwest in Italy, the Senckenberg Castle in Switzerland, and the cellar town of Baltanas in North Spain. So we are including 5 pilot sites across Europe, very different in typology. We plan to integrate Earth observation sensing, on-site sensing, to deploy risk-oriented digital twin platform, and to support for preventive preservation decisions, which is one of the key points in ARGUS. So since ARGUS began at the end of 2024, we are near finishing the project. So a lot has been done so far. Where we are today, regarding each of the components and statuses today. Regarding the sensor deployment, this is a task completed. Regarding the satellite and Earth observation data and products, they are all operational. Regarding the backend platform and APIs to access data and exploit the wealth of multimodal, multi-scale data, we are in beta testing already. Regarding interfaces and front ends, we have our prototypes, and we are testing and putting them to stress test in order to move further to beta testing. Regarding live monitoring, it has already been demonstrated through simulations and the first data collected already. We are still ongoing on predictive models and the final decision support integration that we are going to include and deliver in ARGUS. But this is not far from being actually tested. So regarding the operational monitoring infrastructure, our major achievements include the multimodal sensing packages deployed across the 5 pilot sites. We are discussing more than 100 sensing devices deployed across the heritage sites, the pilots. The environmental and structural and operational monitoring has been integrated. We used LoRaWAN and Wi-Fi communication infrastructures, and they are already operational. We are actually doing live data acquisition through the ARGUS backend systems. So we have continuous streams of data flowing from the sites to the backend systems. We are dealing with thousands, nearly millions of data already collected, and we are even at not the very far from the initial stages. And we have the first API services available for exploitation, usage, and even we started designing a hackathon based on the data we are collecting. We're discussing about a really multimodal monitoring ecosystem in Argus. You can see here the wealth of data flowing, environmental data, weather station, air temperature, relative humidity, wind parameters, solar radiation, rain, soil moisture and temperature, water potential, gas sensors. We have structural measurements, crack meters, tilt meters, GNSSs, vibrometers, also operational systems for visitor counters, traffic monitoring, multispectral imaging. And on the other side, of course, we have the satellite data integrating the solution that we are dealing. But one of the major lessons learned is that sensor deployment, although it seems trivial, is not a solved and so trivial engineering problem, because in real world situations, installing sensors is not so straightforward. Here are some indicative issues, challenges you have to face when you are installing monitoring systems: corrosion, vandalism, power failures, connectivity challenges, renovations happening that change the geometry, let's say, of the access, cable failures, permission challenges, vegetation, harsh environmental conditions. So these are very important factors you have to keep in mind. And these all actually happen to us. Okay, so you have to be careful on that. Regarding the integrating in situ monitoring and Earth observation product data and products, we have already implemented the Earth observation products and ground sensor integration into piloting integrated environments. You can see a screenshot of what we have so far. It's a system, a front-end system. I will show it to you later, that demonstrates how we envision the final user interfaces in Argus. Of course, what we have done was a careful planning of what types of sensors, depending on the threats faced each of the pilot sites. We actually devoted a lot of time in designing exactly which sensors and where to put them. And we ended up geo-referencing everything. So we have in layers on Google Earth all the sensors and the locations they were installed in all of our 5 pilot cases. I will also be able to show you later. But what we do actually in Argus is we try to move from measurements to knowledge and heritage intelligence. So what does it mean? It means that from environmental, structural, and operational sensors and wireless networks, we move to the Argus backend systems, heavy loads of data, which are made available through the APIs to front-end platforms, and create the heritage intelligence needed for the experts, the general public, the authorities, and the owners. Looking at it from a different perspective, it's like moving from measurements to understanding events, to using some policies to understand if events become threats, to assess risks, and to provide recommendations for predictive measures. And then from data, we can move to models, of course. So in Argus data are MQTT sensor streams or Earth observation products, or even historical and conservation records. Those are all inputs to models like erosion susceptibility, flood susceptibility, landslide susceptibility, climate deterioration indicators, which through computational models become the intelligence part of ARGUS. What we do is we try to transform GIS workflows into purely Python-coded models. Models become reusable computational components, and predictions become machine-readable because we heavily rely on international standards in all our steps through our processes. So the system starts moving from data management to environmental understanding. And then from models, next step is to go to reasoning. Multiple predictive models can be combined to evaluate interacting threats and support conservation or preservation decisions. You can understand that models answer specific questions like, is erosion likely to happen, or is flooding likely? Reasoning combines models and answers different questions, like which event is becoming a threat or which threat is becoming critical. So you can understand how reasoning escalates the questions that can be answered. Reasoning emerges from multiple models and their combinations, using also memory, semantics, and context, of course. So lessons learned from real deployments in ARGUS. Every heritage site required a tailored monitoring configuration. Although we started from the same ground, environmental conditions strongly influence sensor reliability. You have to keep that in mind. Low power wireless communication enables monitoring of remote sites. That's a good outcome, although with some challenges, but it can be done reliably. Data integration is often more challenging than sensor deployment, and continuous monitoring provides evidence that cannot be obtained through periodic inspections. So we envision to move towards heritage intelligence, which means to use richer Earth observation products or predictive environmental models to do better event and threat detection, to support decision-making using AI-assisted approaches, to engage the citizens, and to open our APIs and data and innovation challenges. What we also design is to move further and surpass the classical digital twin concepts and transform that into heritage world models. This is a new thing that we're considering. If somebody is designing a new heritage world model architecture, this is some kind of a recipe. You move from observations into semantic knowledge. You integrate risk memory, predictive models, but you also have to include agentic reasoning, policy evaluation, and decision support. And usually you should have a closed loop, including all that steps. So pretty much this is the presentation regarding the results from ARGUS. And I can also stop sharing now and share some maybe interesting visualizations to you. I will try to share my browser to show you some of the topics I mentioned here in the screen. You can see the distribution, what we did for our sensors. You can see the distribution of our pilot sites. And here you can see, if you zoom in, the exact locations of all the sensors we have installed. So we have all the information regarding the sensor. You can click any sensor and you can get all the information related to that sensor. All that data are also included in the backend system in the digital twin ontology. So we know the data streams are flowing from each of those sensors, and we know where exactly the measurements were taking. Regarding I mentioned the first versions of our user interfaces. This is just an indication. You see here our case in the San Antonio di Ramverso church in Italy. So you can see here, this is just like a Google Earth similar interface where you have the 3D model on the map. I can show or hide the 3D model. We also have the locations of the sensors installed in this location. I can change the opacity of the model, or maybe I can show you results from satellite models and GIS models that shows the urbanization threat potential back some years. For example, in 2018, or maybe I can just remove that layer. So we can show multiple layers of false colored information on top of 3D models, and you can see how the situation in each of these cases is shown. Here, of course, we can get information for each of the sensor. These are live data coming from the databases. So you can select any sensor, you can see the readings from the database, and you can also get graphs showing the historic relevance, how it goes from previous measurements to today's readings. So pretty much this is what is happening in Argus, and I can stop my sharing my presentation here. Of course, we can have discussions after the presentations. We are open to any comments and questions. And I think we're ready to move to our next speaker, Marta Segovia from ChemiNova project. She's going to present progress in the digitization and monitoring of European cultural heritage threatened by climate change. So the floor is yours, Marta.
Thank you, George. I'm going to share my screen. Do you see it okay, properly? So hello, everyone. Good afternoon. As George said, I'm Marta, one of the ChemiNova project's conservation team member. And today, as you can see on the screen, I'm going to present progress in the digitization and monitoring of European cultural heritage threatened by climate change. Before we get started, I would like to say thank you to Argus for hosting this webinar and for giving us the opportunity to be here. Moving straight into the topic of the talk, the very first thing is to explain what ChemiNova is. ChemiNova, whose full name is Novel Technologies for On-Site and Remote Collaborative Enriched Monitoring to Detect Structural Chemical Damages in Cultural Heritage Assets, is, like the other sister projects on the cluster here today, a Horizon Europe 2024 project. The core concept of ChemiNova can be summarized in a central idea that connects our four fundamental pillars: how new technologies improve the analysis, monitoring, and conservation of cultural heritage threatened by climate change and armed conflict. These blocks do not operate independently. Instead, they work in an interdisciplinary manner. The project is based on the collaboration of teams from different fields: chemistry, conservation, art history, technology, all of them working together toward a common goal. Furthermore, it is not only focused on generating resources for professional use. The interdisciplinarity that backbones ChemiNova also aims to break down the barriers of traditional teams and to integrate citizens. Through citizen science, people from local communities will be able to use these new tools to protect the heritage of their own surroundings. The consortium is composed of 12 partners from different countries: Spain, Italy, France, Germany, Austria, Romania, Ukraine, and Greece. It is made up of five universities, as la Universidad de Valencia, Universidad degli Studi di Palermo, a research institute, an NGO, 2 museums, 2 private enterprises, and intergovernmental institution. The work has been carried out across 4 pilot sets, one in Valencia, Spain, one in Palermo, Italy, one in Vienna, Austria, and one in Kiev, Ukraine. All of them were selected based on their specific needs, aligned with the project's overall methodology. This is seen, for example, in the case of Kiev, due to the ongoing war in Ukraine, or the additional works included in Valencia pilot after the data of the 29th of October of 2024. Having existing information on the components has been essential to quickly begin implementing the technology alongside the acquisition of the specific data required for each site. Specifically, the acquired data consists of, on one hand, 3D models generated with photogrammetry or LIDAR, which provide the geometry and an initial RGB texture. And on the other hand, multiple non-invasive techniques are performed, such as hyperspectral imaging, reflectance transforming imaging, multiband imaging, infrared thermography, and X-ray fluorescence. The data obtained from each of these techniques will be projected as textures onto the 3D model geometry, thereby creating different layers of information. For example, in this slide, you can see the 3D model of the Sisu with the X-ray F texture, and you can observe the different points that were measured in the object, and as well you can see in the upper part the concentration of elements in each of them. Also, in this slide, you can see one of the bands of the hyperspectral imaging applied in one of the models from the University of Palermo. And for example, also here you can see a detailed view of an RHB texture. Building upon this work, we are creating new digital tools focused on interactive and collaborative cultural heritage conservation. These are ChemiPortal, ChemiEye, ChemiAnalysis, ChemiSee, ChemiSensing, and ChemiInspecting. All of these tools are powered by a centralized database that houses all the assets information. And thanks to this integration, all acquired data can be seamlessly visualized across the entire suite of tools. The first one, ChemiPortal, is the ChemiNova application dashboard from which the users can access to the various tools, and is also where the user will be able to add the different cultural heritage assets. For instance, as you can see at the right part of the slide, it will display the location of each element on a map. Also, the objects can be viewed grouped by collections, by pilots, or individually. Its items, its dedicated section houses all its comprehensive data, including the 3D models, the condition reports, or the condition assessments. Additionally, the application features advanced search capabilities to locate an object faster. The users will be able to filter by location, by materials, by alteration forms, by the state of conservation, and any other items. The next one, ChemiEye, is a platform for automated predictions and characterization of structural chemical damage based on integrated data from various sensors within a 3D mesh. This one of the tools currently is under development as we continue labeling data to train the AI and improve the accuracy of its prediction. It has been deployed in buildings such as, in this case that you see in the slide, that is the roof of the historic Lanao building at the University of Valencia, and also in paintings, as you can see here, that this example is artwork called Tendur that was affected by the Dana here in Valencia. The damage mapping has been conducted using geographic information system softwares like QGIS, and within this software, various information layers are generated to group damages, integrating all the performed techniques to locate alterations that are not visible to the naked eye. Moving to the next one, chemianalysis is a non-invasive, non-destructive optical method for analyzing the state of preservation over time. And this tool is designed for target inspections and chemical analysis, enable a deeper study of the materials. And one of the features currently under development is the ability to view the hyperspectral imaging spectra. Additionally, by downloading the various condition assessments that are the data acquired in different moments about the same object, users will be able to compare the assets across its different states over time. ChemiC is an immersive experience designed to connect the public with cultural heritage and the impacts of human-induced threats. And this tool aims to engage the general public by exploring the pilot projects, encouraging people to notice the artwork's materials and degradation patterns, that they are details that usually go unnoticed. Next one is ChemiSensing, that is a platform for synchronous collaboration for remote monitoring in a mixed reality environment. In this one, multiple users can work simultaneously while communicating, like through an audio channel. It features multiple functionalities, including a laser point, measurements, inspection by layers of information, and the ability also to bring other users to your point of view. What is very useful, because if you see something important, you can conduce them to the exact point where you are, and they don't have to search it. Here we have a video that demonstrates Connect the user interacting with one of the models. As you can see, is rotating the 3D model. Is pointing with the laser to show which one is seeing. Again, rotating. Again, pointing with the laser. Now, as you can see, it's measuring. And that's it. I think we can move on. And last but not least, there is ChemInspection. It is an on-site synchronous collaboration platform for experts using augmented reality to generate conservation reports. It is also collaborative, allowing users to make annotations, take measurements, and adjust scales, but on-site. Through image or object tracking scans, users can work with the model and its various information layers directly in front of the physical artwork. At the same time, it can be used for a more visualization from home using the 3D model upload in the Chemi portal that was the first tool that I explained. Within the application, users can review condition reports, inspect items using augmented reality, interact with the models, and access to all the related documentation. And that's all from me. Thank you so much for the attention, and I will be so happy to answer your questions at the end of the webinar.
Okay, thank you. Thank you very much, Marta, for this very interesting presentation on the work being done in ChemiNova. Very interesting. And I like the thing that you do, that you name your tools with a chemi and something. Yes, that's very interesting. So maybe next stages or in next project you can use those tools and bring them to high TRLs or maybe even products in the market. So that's very important also. I hope everyone is taking notes for questions later after we finish the presentations. And without further ado, I will move to our third presentation. Thank you, Marta. We will move to Elena Telegrafou from NERITES. She's going to present us bridging underwater cultural heritage protection, marine monitoring, and policy needs. Elena, the floor is yours. Please do share your presentation.
Thank you. Thank you very much, George. I'm sharing the screen. Please let me know that everything works well.
Yeah, it's perfect.
I see. Thank you. Good afternoon, everyone. Good afternoon from Greece. Thank you, George, very much for the introductory. And of course, thank you to the ARGUS project for the opportunity to present the NERITES within this webinar. My name is Elena Telegrafou, and I am an archaeologist, and I am currently working in Atlantis Consulting. We are partners of NERITES project and responsible for the communication and dissemination work package. Today, I will present NERITES and actually how NERITES connects underwater cultural heritage protection, marine monitoring, and policy needs. This is very relevant to the topic of the webinar because NERITES is not only about collecting data, it is also about how this data can become useful knowledge for monitoring, for conservation, for planning, and for decision making. About the need, as we all know, underwater cultural heritage includes shipwrecks, submerged archaeological remains, ancient ports, artifacts, and other cultural assets located underwater. These sites are extremely important for understanding history, understanding maritime routes, trade, and of course the long relationship between people and the sea. But they are also very difficult to monitor. Traditional underwater surveys usually requires divers, vessels, specialized equipment, and repeated field campaigns. And this makes monitoring very expensive and sometimes very risky. At the same time, these sites are exposed to many pressures, such as environmental changes, marine pollution, biological colonization, tourism impacts, and climate change. So there is a clear need for monitoring solutions that are autonomous, robust, non-destructive, and more cost-effective. So this is exactly what NERITES comes to address. NERITES aims to develop autonomous and reliable methods for detecting chemical, environmental, and geophysical indicators while reducing both the operational and capital costs of underwater heritage missions. So the vision of NERITES. The vision of NERITES is to support the systematic and remote monitoring of underwater cultural heritage sites through the advanced technologies that the project develops. In simple terms, NERITES aims to create an integrated system that can operate underwater, collect useful data, assess the condition of cultural heritage assets, and support better decision-making for their protection. The non-destructive character of the technologies is very essential. So when we work with underwater cultural heritage, the goal is not only to study these sites, because they're already studied through the archaeologists, but to preserve them, to monitor and preserve them. So this connects directly with today's theme, moving from heritage data to heritage intelligence. So data alone is not enough. What matters is how this data is collected, processed, interpreted, and used. So the motivations of the project are the well-known outcomes of the ocean decade. The project is aligned with these broader international priorities for the ocean, and contributes to the idea of a clean, healthy, resilient, and accessible ocean when data and technologies can support better understanding and protection of the marine environment and of the underwater cultural heritage, which is also part of this. About the partners, a key element of the NERITES project is the stakeholder engagement. The project brings together different types of expertise. Some partners are involved in archaeological research, historical analysis, and cultural heritage preservation. These partners are help NERITES to define the real needs and requirements of the system that is going to be developed. And of course, the other partners are responsible for developing the technological components of the system, including the autonomous platform, the sensing technologies, the image processing tools, the communication systems, and of course the data analysis tools. This combination is very important. A monitoring system for underwater cultural heritage cannot be developed only from a technological perspective. It must also respond to archaeological conservation and management needs. About the key objectives. The NERITES project has 5 main key objectives. The first is the remote monitoring. The project aims to develop autonomous system that can support the monitoring of underwater cultural heritage sites without requiring human presence underwater. The second objective is the preservation assessment. NERITES will help assess the conditions of underwater monuments and artifacts and provide useful information for conservation and management decision. And the third objective is the development of an alerting mechanism. This means that the system is able to detect specific changes or risks and support interventions when needed. The fourth objective is to provide a cost-effective solution, reducing the need for repeated diver-based campaigns and lowering operational skills. And finally, the fifth project is to support greener solutions, of course, aligned with the European policy priorities. About the core technologies, NERITES combines several core technologies into one integrated system. The first one, the basis, is the AUV, the autonomy platform, which supports autonomous underwater navigation and data collection. The second is the docking station and the charging buoy, which is very important for the long-term operation of the system. It integrates renewable energy and communication systems, allowing the platform to recharge and exchange the data. The third is a group of sensor technologies, advanced sensor technologies such as the LIBS and the QCL. The LIBS, or laser induced breakdown spectroscopy, can provide information and support both environmental and archaeological analysis. And the QCL, or the quantum cascade laser technology, is also used for sensing and detection purposes. Another important component is the advanced image processing. AI algorithms are used to analyze underwater imaging data, which is especially important because underwater images are often affected by low visibility, light distortion, and complex environmental conditions. And finally, NERITES also uses a 4D analysis of photogrammetric 3D models. This means that 3D models of the same site can be compared over time, helping experts to detect some changes, some degradation, or movements of the underwater heritage sites. All these technologies are being developed and integrated in order to provide a more complete picture of the system and the condition of the underwater cultural heritage sites. At this stage, NERITES is in its integration phase. This means that all the specific technological components that described before are being interconnected and tested in laboratory pools. And this phase is also important and prepares the system for the upcoming pilot demonstration and the two NERITES pilot sites. As you can see, the blue part is the LIBS, which described before. This is the whole system, the AUV, where all the specific technological components will be integrated. And here you can see a picture of the camera and the light, which will also help for the photogrammetric analysis of and the production of the 3D models of the underwater cultural heritage. So, about the pilot sites of NERITES. The first pilot site is Fourni, located in the Aegean Sea, Eastern Aegean Sea. Fourni in Greece. Fourni is a complex of 20 islands and islets with major historical significance. It is especially known for the high number of shipwrecks identified in this area. Since now, more than 58 shipwrecks have been identified, which is the 23% of the identified shipwrecks in Greek waters. As you can understand, Fourni is a Mediterranean treasure. And NERITES pilot operations will focus on the Aspros Kavos area, where there is a high number of wrecks, mainly composed of ceramic and metallic materials. And the second pilot site is the archaeological park in Baia in Italy, located in the Bay of Naples. Baia is one of the most important submerged archaeological site in Mediterranean. It includes maritime infrastructure, baths, mosaics, and other architectural remains. In Baia, NERITES will focus in the Villa dei Bisogni, a well-preserved submerged complex with mosaic pavements and other construction materials. As you can see, the two pilot sites are very different. Aspros Kavos is a deep water site with visibility difficulties, while Baia is at the depth 4 to 5 meters. And this, of course, allows NERITES to test its system in two different contexts. The pilot testings will take place first in Baia in late August, and after in Fourni in late September. So we are currently preparing the system for the pilot demonstration. NERITES also has identified some policy gaps and needs for the underwater cultural heritage. As you can see, the project also connects the technological work with the policy dimension. Underwater cultural heritage faces several policy and operational gaps that limit its effective protection and sustainable management. One important gap is the limited integration of underwater cultural heritage into maritime spatial planning and blue economy strategies. This means that cultural heritage is not always sufficiently visible in wider marine planning and decision making. So, yeah, there's also a need for greener, safer, and non-invasive monitoring approaches because underwater heritage sites are fragile and are often located in sensitive marine environments. Furni is a great example of this thing. Another need is the stronger use of data, AI, and robots in heritage monitoring. These technologies can improve documentation, support repeated observation, and help experts to understand changes over time. And there is also there are also fragmented frameworks for underwater archaeological research, documentation, and long-term monitoring. And finally, there's a need for stronger collaboration between cultural heritage, marine science, technology, and policy actors. These gaps show that heritage monitoring is not only a technical challenge, it is also a policy and governance challenge. Based on this approach, NERITES supports policy actions to strengthen the protection of underwater cultural heritage. So first, NERITES highlights the importance of integrating underwater cultural heritage into maritime special planning and blue economy strategies. This can help ensure that underwater cultural heritage is recognized as part of marine planning and not treated as an isolated issue. And second, the project supports non-invasive, cost-effective, and environmentally friendly monitoring methods. These methods can reduce risks for divers and reduce the environmental footprint of monitoring activities. Third, NERITES supports the responsible use of AI, of technologies, robotics, and advanced data analytics for heritage preservation. And these tools can help also transform monitoring data into actionable intelligence for experts and decision makers. Fourth, stronger frameworks for underwater research, innovation, and long-term monitoring are being recommended from the project. And finally, NERITES encourages cross-sector collaboration between public authorities, researchers, technology providers, and heritage stakeholders. So in this way, NERITES contributes to turning heritage data into useful knowledge for better protection, planning, and decision making for the underwater cultural heritage. So this was everything for me. I'm very happy and open for questions if any. And thank you once again for the opportunity to present the project within this webinar.
Awesome. Thank you very much, Elena. That was a very, very interesting presentation. And always underwater heritage protection is a very exciting topic, totally different to what most people do, and with very specific challenges, of course. You have to deal with another medium, water, and especially seawater, whatever it means, for doing work in such an environment. Everybody knows it's so much challenging. So please, everyone in the audience, keep notes. We are expecting more questions for this topic. Thank you again, Elena. We are moving on to our next presentation from Eliana Pirianaki, the iPhotoCult project. Ileana is with us to present non-invasive photoacoustic imaging for in-depth cultural heritage diagnostics. Ileana, if you're ready,
Hello. Yes.
You have the floor. You can share your presentation.
Please tell me if is everything
Yep.
okay? Okay, great. So, hello everyone. Thank you for the opportunity to present to you our work entitled Non-Invasive Photoacoustic Imaging for In-Depth Cultural Heritage Diagnostics, which is being carried out within the framework of the European project iPhotoCult at the ISL laboratories at Forth. Well, to begin with, I think it is useful to see some theoretical background for the photoacoustic phenomenon so we can understand it better. So, the photoacoustic effect is the generation of acoustic waves following the absorption of the optical radiation by a medium. This is the equation of the initial pressure, where, as you can see, it depends on absorption coefficient of the medium, the fluence of the laser, and the Organised parameter. Moreover, and the most important thing, is that the sensitivity of the photoacoustic effect is up to 2 orders of magnitude higher compared to the one that optical techniques can offer, and the photoacoustic signals compared to NIR or visible ones present up to 3 orders of magnitude improved transmission through turbid media. But okay, what is the added value of the proposed technique compared to the ones that already existed? First of all, the photoacoustic system is portable and suitable for in situ measurements in galleries and museums. Secondly, the photoacoustic system is easy to assemble and operate even for non-experts. Moreover, the photoacoustic system enables deep probing on optically diffusive media thanks to ultrasonic wave transmissivity. The photoacoustic technique offers much higher optical absorption sensitivity than conventional optical spectroscopy. And last but not least, the photoacoustic technique can detect ultrasonic signals with transducers placed several centimeters away from the sample, maintaining the non-invasive nature of the technique. Now, the main goal is, of course, to investigate the applications of the photoacoustic effect towards the in-depth diagnostics of cultural heritage objects. In order to do that, we have performed photoacoustic measurements on 4 big categories of cultural heritage items, which are paintings and frescoes, papers, metals and alloys, and inks. More specifically, our measurements focus on the identification of pigments, metals, coatings, and historical links, the assessment of aging and corrosion processes in metals, papers, paints, and varnishes, and as well as the revelation of hidden underdrawings in frescoes and paintings. In order to do that, we have created the following experimental photoacoustic setup, which consists of a pulsed laser emitting at both 1064 and 532 nanometers wavelength. It follows a filter wheel with 2 colored glass filter in order to select the desired wavelength. Then the desired wavelength meets the surface of a broadband dielectric mirror, which directs the beam on the surface of the sample or the mock-up, which is placed and secure at the surface of 2 motorized stages in order to be raster scan. Then the generated photoacoustic waves are detected by an air-coupled spherically focused ultrasound transducer, which is placed almost 1 centimeter away from the sample. And then the photoacoustic signals are amplified and digitalized with the help of an oscilloscope. And a PC controls and synchronizes the whole dual wavelength photoacoustic setup. Now we're moving on to the first big category of cultural heritage objects, which are paintings and frescoes. Here we present the fully non-invasive revelation of hidden underdrawings based on work published in 2024. For this study, we used only 1064 nanometers excitation wavelength, since graphite, which is the most common mean in order to create underdrawings, is strongly absorbed in this region. So to do that, we have created some series of mockups. The first one is a canvas mockup with an outer drawing, as you can see. We covered this outer drawing with titanium white acrylic paint, and after that we applied a layer of acrylic varnish. The sample was imaged with both photoacoustic imaging and multispectral imaging in order to compare these two techniques. The multispectral is the state-of-the-art technique for this reason, for this occasion. You can see here that the photoacoustic technique provides clearly superior imaging contrast compared to what multispectral imaging can offer. But there are cases that the varnish is absent. In that cases, unfortunately, photoacoustic imaging cannot give any imaging contrast because of its nature. But we have the solution. We have created here another series of mockup with gypsum substrate this time. And we have created a gelatin gel that can easily be applied with a syringe and removed by hand, causing not at least visible damage, as you can see from the microscope image, before and after the application of the gel. And the most important thing here is that, again, the photoacoustic technique offers significantly enhanced imaging contrast compared to the one that the multispectral imaging can offer. Now, within the same study, we investigated the ability of the photoacoustic technique to detect aging phenomena in artificially aged paint samples. So, we created another series of mock-up. This time it was ochre yellow with a binding medium of egg yolk, and we used glass slides in order to create those mock-ups. And we artificially aged them for 2, 4, and 6 hours respectively under stable conditions of 65 Celsius temperature. And we kept one as a reference sample. Then we took 10 spot measurements using only 1064 nanometer wavelength on the surface of each one of these mockups, and we calculated the mean peak-to-peak amplitude from each one. And as you can see, the average photoacoustic amplitude showed an increase with aging time, as you can observe from the figure E. But if we look at the figure F, we can see that from 4 hours to 6 hours, there is a saturation tendency, a tendency to saturate, which is in a great agreement with the literature, because ochre yellow is supposed to be a very stable pigment. But all these peak-to-peak amplitudes depend on pigment concentration, and we need to find an objective pigment degradation measurements unaffected by the pigment concentration. For that reason, we have established a calibration protocol using black tape as a phantom, and we adjusted the energy of each wavelength, 532 and 1064, so that the peak-to-peak amplitude of the photoacoustic signal, as you can see here, generated from the tape, produced a ratio that is equal almost to 1. So we radiated the phantom at 10 different places with 532 and 1064 nanometers wavelength, and then we calculated the ratios and the mean ratio, and we tried to succeed a ratio almost 1. Now, here we present results from the dual wavelength photoacoustic spectroscopy system currently under, it's a work that it is currently under review. And we created another series of egg yolk ochre yellow samples, and half of each sample was was uncoated, and the other half was covered with damar varnish. Those samples were photo-aged for periods that it is equivalent to 10 and 25 years of natural aging, with one sample kept again as a reference. And we followed the exact same procedure that we have already described. So, as you can see from the uncoated region, we have an increase in the photoacoustic signals in the visible range, 532 nanometers, indicating aging-related pigment changes. But in contrast, we can see in the coated region that we have an increase in 1064 nanometers wavelength, possibly related to the yellowish of the varnish. While the visible photoacoustic signals in 532 nanometers wavelength remain stable, highlighting perhaps the protective role of the varnish. This behavior is also confirmed by the ratio of these amplitudes, where the uncoated region shows an increase, and you can see, and the coated region an decrease. So we have performed on the same samples measurements with nonlinear optical microscopy measurements, because with this technique we can additionally determine the depth to which the degradation of the varnish has progressed as a function of artificial aging time. And you can see, as shown in the graph, the fluorescence signal increases with aging time, indicating the gradual progression of varnish degradation for the damer varnish. Our second big category is inks. Now, identifying inks used in historical document is essential because it helps us design the right restoration strategy and gives us important clues about their authenticity, origin, and dating. For this reason, we have used three types of inks that were used in Greece around 19th century. As you can see, Chinese ink, sepia ink, and metal gall ink. And for each ink, we have used three different pen types. So each region was imaged with both 532 nanometers wavelength and 1064 nanometers wavelength. And in the third column of each ink table, you can see the ratio image. But how we achieved to take the ratio images? We needed an automated and objective identification method of ink regions versus background for the accurate quantification of the photoacoustic signal ratios. So we used K-means, which is a machine learning algorithm which selects regions of the images with strong signals and using them to extract the ratio images. And as you can see from the ratio graph, regardless of the different pen types, the photoacoustic technique can distinguish the type of ink by extracting a characteristic ratio for each one of these three. To be more precise, we have Chinese ink with a ratio almost 0.9, sepia ink with a ratio almost 0.6, and iron gall ink with a ratio almost 1.7. So the photoacoustic technique can differentiate between various types of inks independent of the writing method or ink concentration. The third big category is papers. Okay. So for those measurements, we have used craft wrapping paper, 4 pieces of that paper, and we have artificially aged them for 7, 14, and 28 days under stable conditions of 80 Celsius temperature and 78% relative humidity. As you can see from the amplitude graph and the ratio graph, as the aging time progresses, the ratio of the photoacoustic signal decreases, meaning that the photoacoustic technique can detect the early stage aging phenomena on papers. The last category, last but not least, is metals. So here I focus only on the measurements. The measurements here are just a small part of an ongoing study on more than 30 metallic samples with different substrates and protected varnishes. The samples were progressively photo-aged to simulate 10, 20, and 30 years of natural aging. The study combines measurements with photoacoustics, nonlinear optical microscopy, FTIR, and colorimetry. Here I focus only on 3 samples with the same polished silver substrate, but different coatings. As you can see, we have Frigilen varnish, Incralac with matting agent, and Renaissance wax. So what we see here is that the photoacoustic signal increases after aging, especially for the 532 nanometers wavelength, indicating that the technique can detect both the corrosion of the metallic substrate and the varnish degradation. Since the signal evolution differs between coatings, for example, we can see that the fridge length we can reach at almost 25 millivolts for 20 and 30 years of natural aging, while with Incralink without mitigation, we cannot pass 9 millivolts. And Renaissance Works has a gradual increase in the photoacoustic signal, but it becomes more dramatic after 30 years of natural aging. So that means that the photoacoustic technique may also be used to evaluate the protective efficiency of varnishes on metallic surfaces. Moreover, we present the imaging measurements performed on metallic substrates, but with and without a protective coating later. As you can see, corroded areas in various substrates exhibit different photoacoustic amplitudes compared to clean ones, allowing their distinction during imaging at 1064 nanometers wavelength. And the presence or absence of varnish in both corroded and clean areas can be distinguished because we have negative contrast in the regions where we have varnish as the photoacoustic signal attenuates significantly. To conclude, the photoacoustic technique is capable to detect aging-related phenomena in many cultural heritage items, is capable to detect the presence of absence of varnish with spatial resolution better than 800 micrometers. There is also strong evidence that the photoacoustic technique can differentiate between various types of metals, alloys, papers, inks, and pigments. It presents up to 2 orders of magnitude higher sensitivity compared to standard absorbance measurements. And the photoacoustic imaging contrast of paint over underdrawing has been at least 2 times higher than the one provided by NIR images. And last but not least, the photoacoustic signals compared to NIR or visible ones present up to 3 orders of magnitude improved transmission through turbid media. For our future plans, we want to validate the technique's sensitivity to aging-related phenomena by using many different cultural heritage items as samples. Moreover, we want to test the detection capability of the technique of functional contamination in paper samples. Also, we planned measurements on aged inks in order to attempt an assessment of the alterations that may exhibit. But the most important is the development of a portable photoacoustic spectroscopy prototype for in situ measurements in museums, galleries, and archaeological sites, which is something that we have already begun to design and construct. Thank you very much. I want to thank my colleagues at Forth. Thank you very much for your attention.
Well, thank you. Thank you very much, Liliana, for this very scientific, I would say, presentation and the in-depth insight on what you are doing in photoacoustic imaging for diagnostics of heritage assets, objects, and various media, actually. It was really educative for me, at least. I hope it was good for everyone. And this concludes our round of talks. Everybody heard about ARGUS and remote heritage sites, how in ARGUS monitoring is envisioned to go to intelligence. And then we moved to ChemiNova, where you heard about specific processes for protecting threatened heritage by climate change through very specific approaches and tools being developed already. And then we moved underwater. We saw how things are going in underwater heritage protection. And we finished this round of talks with photoacoustic imaging and applications in the heritage diagnostics. I think it's time for some questions. So if there are any questions, I don't see any questions in our chat yet. Okay, for iPhotoCult, there's the first question. What improvements are still needed before the widespread adoption of the photoacoustic technique? And how does this technique compare with other techniques such as Raman and FTIR?
Okay. Thank you for this question. First of all, we want to expand our samples using not only mockups or high control real case samples. We need to test the capabilities of the technique with real samples with high complexity, of course. And moreover, another idea could be transducers with all optical detection. For example, optical fibers, which are more compact and less expensive and with high resolution. Of course, we need to build a portable system that could be easily transferred and stored while also being simple and relatively affordable. And perhaps we can use lasers and emitting at more than 2 wavelengths in order to achieve really true multispectral photoacoustic spectroscopy. Now, for the second part of the question, for the FTIR and Raman, to begin with, photoacoustic technique cannot give any chemical information, something that Raman and FTIR can give. But photoacoustic technique can give only optical absorption information, which of course is related to aging phenomena. But on the other hand, it has enhanced sensitivity and it can detect alterations that FTIR cannot. For example, when I showed you the graphs for the metals, the aged metals, we can observe alterations in the signals up to 200%. And for the same samples, we have performed measurements with FTIR and colorimetry, and those techniques cannot give any alteration. And also there is a possibility for a mid-infrared photoacoustic system, which could provide chemical information, but it may be challenging due to less sensitivity, perhaps, or higher cost. Thank you.
Okay, thank you very much. It's actually a very interesting approach. I have been experimenting from the data science aspect with Raman spectroscopy also, because the spectra we get from that method are extremely noisy, skewed, and everything. So you have to do some kind of housekeeping in the data and then apply methods to actually recognize what you see hidden in there. But in any case, thank you for that. If we have any more questions, please do paste them in our chat. Let's move to NERITES, which is a very, very, very different environment, very challenging environment. In NERITES, practically, where do you see the strongest challenges in reliable monitoring and data collection underwater? It's a major concern. What are your thoughts on that?
So thank you, George, for the question. To be honest, practically the pilot demonstration have not been conducted yet. So we hope that we won't have any problems in the upcoming months. But to answer your question, not to the underwater environment, but during the process of the development of the technologies, we are facing some problems in the integration phase. So when you have so many separate a specific technological components, that all these must be integrated into one system, of course, you can imagine that there will be some problems. But underwater, yet, the system is only tested in laboratory pools. The thing is the process, it works well. But during the pilot demonstrations in the upcoming months, we hope we won't have any problem. But from past research projects that are similar, I think the underwater environment has many challenges, as you may imagine and understand. So the big challenge is the water conditions. So and the weather conditions. So we hope for the best for the upcoming months. So yeah.
I also wish you the best, because I know that you have many unforeseen parameters also, the weather, the conditions and everything.
Mm-hmm.
Okay, let's continue with NERITES, and let's try to respond to a question in the chat. Everybody in all projects, we are dealing with diverse data. Multiple modalities, totally different frequencies of getting data, different ranges. Everything is so diverse. How do you harmonize everything into a single decision support framework? Everybody is trying to get a multitude of diverse data and try to do something with them in order to reach a point to suggest something for the protection of the site. So how do you deal with that?
So NERITES is a very diverse project because, as I said in my presentation, it contains partners from different expertise, partners that has expertise in archaeological research, and partners that are very technical, and they are developing the technological components. So I think the communication between the partners during the development process is very important. For the project to develop a technology that address the needs of an archaeological, the real need of an archaeological site. Yeah, it's a big challenge, but I think the communication between partners before developing a technology, this makes the project interesting, difficult at the same time, but interesting because the collaboration between different partners and different expertise makes the project interesting and successful as well. So I'm not sure if I answered the question.
Yeah.
But regarding NERITES,
Yeah, got it. Yes. Okay, same question for everyone. So please, Iliana, maybe for iPhotoCult. I think you are mostly presented as not so much of diverse data, but a very specific method with very specific data. But I suppose you also do in iPhotoCult a lot more. So you collect a lot of diverse data. And I don't know if you can answer a question about harmonizing those different data coming from different sources, different sensors on the same asset, in order to maybe reach a better conclusion than just using one sensor.
Well, we have, as I told you before, we have collaborations with other techniques also, like nonlinear optical microscopy, FTIR, and colorimetry. So I think I can describe you some challenges using all of these techniques in order to extract some conclusions. So regarding the photoacoustic technique, I think the main challenge is related to the fact that Each analytical method from the ones that I told you has a different resolution and provides different types of information. So we need to discuss and combine these results in order to obtain a reliable outcome. And moreover, the mock-up sometimes have to adapt it to the specific requirements of each technique, although the photoacoustic method itself is not very demanding. And moreover, another important aspect is that we need to have very good communication and collaboration with conservators and scientists who have a deeper knowledge of the artworks and the materials, because in this way we provide the more technical information with our method from our method, and we can properly collaborate and discuss it, and in order to extract the desired conclusion. I don't know if I answered.
Okay, perfectly. Thank you very much. And then let's move on to Marta. And I didn't get the name of your colleague, Marta.
Carmen.
Okay.
For us, it's more or less the same as for the other projects. Our problem is that we are using many techniques with really different resolutions, because our hyperspectral camera has a really low resolution, and we have to try to project all the techniques in the same 3D model. So it's being a little bit difficult for the techniques. Actually, Marta and me, we're conservators, so we don't know how they are doing the whole process, but they are doing it, and we finally have a product, because the photogrammetry, it's a really high resolution technique, and with the multiband imaging it happens the same, but they are enhancing in some way the other techniques, and they are doing it really great.
Okay. I should complement your questions with what we are doing in Argus, just to complete the picture. So in Argus, we have a proactive approach and a reactive approach. So the proactive approach is that we designed everything from scratch using international standards. So what we designed in our data management plan at the beginning of the project was a plan to collect data and transform everything into international standards, so that we know exactly the format of all the data that we're going to collect. Nevertheless, in practice, when you start collecting data and you actually use sensing devices, data from satellites and all that stuff, you realize that the data are not collected with the same resolution, same accuracy, same precision, same frequency, same time frames. I don't know, everything is totally different. The scales are different. I mean, imagine that you can have, for the same site, satellite data for which 1 pixel of a satellite picture is something like 100 by 100 meters. And then at the same time, in the same region, you have a sensor measuring temperature at a very specific point. So the point is another pixel in another picture. So you have to have ways to be reactive, to combine, to fuse, as we say technically, information with totally diverse characteristics into something meaningful, so that we reach conclusions and propose actions. Okay, so what we do is, at first, we designed everything to be collected and transformed to standards, to international standards definitions. And then we try to harmonize all those diverse data using anchor points, let's say, in space and time, so that we align measurements both in space and in time. Because you can imagine, if you get time series measurements from, let's say, weather related sensors and vibration sensors and crack meters and whatever else, they are not aligned in time. Although you can align them in space, they can be one next to each other, but they follow totally different measuring patterns. So you understand you have very, very practical challenges to tackle. In ARGUS, we are considering to tackle the fusion of satellite with sensor data using what is called late fusion techniques. Late fusion techniques refer to using one set of data to predict something, use the other set of data to predict something also, and then you try to fuse the outcomes, the predictions, into a better prediction. So this is something like a very simplified way to present what is called the late fusion. Whereas if you consider early fusion, it means that you have to deal with the data at the beginning as they flow. That's extremely difficult in situations like the ones we face in our projects. So I don't know if that actually answers the question in the chat from all the sides. I mean, we saw that from the technical up to the practical side. So I think we can conclude this meeting, this webinar. Maybe a concluding phrase from all of you, just one phrase concluding, and we can finish. Let's start with NERITES, let's say.
Thank you, George. You want a phrase for the project or just a general remark?
Just a general concluding remark for this meeting.
Okay. For my perspective, I'm very happy seeing all those research projects that are being developed, and I hope my hope is that we will continue to have funding from the European Commission, and of course continue our work, and because the research is very important, and the data and the outputs of these projects are very, very significant. So that's from me.
Thank you very much. iPhotoCult, and then ChemiNova, please.
Thank you for the opportunity to present our works. It was very, very interesting to learn about all these projects. And I hope that in the future that there will be more projects and many, many other interesting things concerning the cultural heritage science. Thank you.
Thank you very much. Thank you. And we are closing with ChemiNova.
So for our part, we want to say that how important is the communication, not only between the different technical parts, but also between projects, because in this way we can learn a lot and to develop more new technologies and to improve them to get a better cultural heritage conservation.
Okay, thank you very much. From my side, I would say that it's a privilege to be in the same cluster with all these very interesting projects. Remember, the four of us, the four projects are in the same cluster, the green cluster for cultural heritage protection. That's very important. This is an initiative in Europe that clusters sister projects, as they say, because they see a potential there that if we collaborate with each other, we can do more than each of us separately. So with this, thank you all very much for participating. Thanks to the audience for being with us, being patient with us, and hearing what we had to say. So thank you all very much. We can conclude this meeting. Thank you.
Thank you very much.